All right, so we're on chapter 4. Chapter 4, looking at the mole and stoichiometry. Have you heard of the term mole before?
I think I heard about it in chemistry class, though, so I really don't remember what it is at all.
All right, now the word stoichiometry is also kind of a new word for us, but we're going to see if we can become familiar with these words a little bit. Okay, first I have a joke for you.
Oh, no.
Oh, you don't like my jokes?
Well, they don't have a good track record so far.
Okay, well, hopefully this one will be better. In the end, you tell me what you think of it, okay?
Okay.
So, this was a joke that I heard as a kid, so if it's good, it's not really my own joke, right? The joke was, what weighs more, an atom of gold? No, sorry, that's not the joke. The joke was...
Not starting off very good.
Just give me a second. The joke is, what weighs more, a gram of gold or a gram of helium?
That was the joke you heard as a kid?
Well, actually, it was a gram of gold and a gram of feathers. But, well, actually, it was a pound of gold and a pound of feathers. But the joke works either way. So what do you think? What weighs more, a gram of gold or a gram of helium?
I've heard something like this. They weigh the same. They're both a gram.
Very good. Very good. They're both a gram. Now, I bring this joke up because when I was a kid, I used to hear it said, or maybe I said it differently. Like, for example, sometimes I would hear, what weighs more, a gallon of gold or a gallon of helium? And what weighs more there?
A gallon?
Yeah.
Well, a gallon is a measure of volume. So because gold has more mass per volume, density-wise, right? That's the density is. So gold is going to weigh, a gallon of gold is going to weigh more than a gallon of helium.
Yeah, that's right. And a gallon of gold weighs more than a gallon of feathers, right? So another bad way to say the joke that wouldn't be correct is what weighs more, an atom of gold or an atom of helium? Because we already know this, right? What weighs more, an atom of gold or an atom of helium?
Well, you said that the bottom number on the periodic table is the mass, right?
That's right. So helium here, 4. Gold, where's gold at? 197. Is that, no. Silver is 197. What does that say down there? Gold is, gold is 197. Silver is 107. So 197 for gold, all right? So yes, just because you have an atom of two different kinds of atoms doesn't mean they have the same mass. And we need to remember that. We need to remember that the masses of atoms are different from each other. Okay? All right, now, as far as volumes of material, that depends on their density, right? If you just have a gram of two substances, then yes, they have the same mass. They both have 1 gram. Now, when we compare the masses of elements on the periodic table, initially, when we were, discovering these elements, we would say that hydrogen, which was identified as the lowest mass, had a mass of what we said 1 unit per atom, right? 1 unit per atom. And then everything else, all the elements, were just kind of given masses of units more than hydrogen because hydrogen was the lightest. Over time, we changed our philosophy and decided to centralize our mass system around carbon. And we decided that if we had 12 grams of carbon-12. Now, tell me, why do I call it carbon-12? Do you remember that?
The 12. Let's see, there's 6 protons in an atom of carbon, so the 12 must be the protons plus neutrons. So carbon-12, 12 is the mass?
Yeah. So if I said I had 12 grams of carbon-12, then I could say I have 1 unit of carbon-12. And this term, unit of carbon-12, is referenced to us by 1 molecular unit. Now, that term molecular Now we know that the term molecular is used to refer to kind of the cluster of the chemical, how that chemical kind of interacts with other chemicals, right? So we say water is molecular. We say that this is the molecular structure. It goes around and does its business as a molecule. Now, how can we tell if a compound's a molecule? This is a little review as well.
You mean by looking at the chemical formula?
Yeah. How do we know that, for example, H2O is molecular, a molecular compound?
Well, because of the nonmetals, right?
That's right. What do you mean the nonmetals?
Oh, hydrogen's a nonmetal, and oxygen's a nonmetal.
That's right. So hydrogen and oxygen are both nonmetals, and compounds that are made of nonmetals interact with each other molecularly. Okay? Interact with their surroundings in units of their chemical formula. And that's why, for example, you'll have chemical formulas like H2O2. All right? This is a molecular formula for a very common compound, hydrogen peroxide. Have you heard of hydrogen peroxide? Okay. Hydrogen peroxide. And notice that it's not in its lowest form. You could say, oh, HO would be the simpler formula for hydrogen peroxide. But for molecular compounds, we don't always put them in their simplest whole number ratio. We always put them in the ratio in which you'll find one molecule of that substance. Okay? So, one molecular unit, they called it, and we've shortened that to now 1 mole. And really, the term molecular unit wouldn't apply to lots of materials because ionic compounds don't behave molecularly. But we still say we have a mole of, you can have a mole of water, you can have a mole of carbon dioxide, which is a molecule, but you can also have a mole of sodium chloride, which is an ionic compound, a salt, right? So you can have moles of anything. You can have a mole of dogs. In fact, the term mole has turned into actually just a number. It's just a number now, okay?
How can it be a number?
Well, the thing is, once we decided that 12 grams of carbon-12 was 1 mole, then we can actually count the atoms of carbon-12 and find out how many atoms there were in there. Then, looking at our periodic table again, we can do the same thing for any atom. If I had 14 grams of nitrogen, I would have 1 mole of nitrogen, and the number of atoms of nitrogen I would be a mole, but the same number as if I had 12 grams of carbon-12. Okay?
How do you count those atoms?
Well, you don't actually, take tweezers and count like that, but you can perform electrical experiments where you oxidize or you react certain materials until they're all gone. And you do this with an electrode. And the electrode measures the amount of electrons that transferred in the process. And from that, you can tell how many atoms there were that released electrons. And you can count the number of electrons, and you can determine how many atoms you started with. So that's how we got our number for the mole. Okay? And this number is 6.023 times 10 to the 23rd. 6.023, or 6.02 times 10 to the 23rd. And like I said, you can have a mole of anything. Cars, dogs, eggs, whatever it is you want. Now, that's a very, very large number, right? A mole of paper stacked on Earth would go to the sun and back lots of times. Okay? So this is a big, big number. If I have a mole of something like carbon, it's not an enormous amount. That's it right there, 12 grams, right? This is my mole of sulfur, my mole of mercury, my mole of iron. So these are normal laboratory amounts that are not unreasonable to work with. Nowadays, we work with generally a lot less because we don't want to just waste material for experiments. But the point is, these are usable amounts. So, what does this mean? Well, it means that this number on the bottom of our elemental box here, our symbol, the number has units, and those units are grams per mole of that given atom. So if I want to get a mole of chromium, I can weigh out 52 grams. Now, why is this a good thing? Because if I want to perform a chemical reaction, like maybe I want to create some carbon dioxide, feed it to some plants, and find out which plants are best at collecting carbon dioxide to battle overproduction of carbon dioxide in the atmosphere, right? If I want to collect carbon dioxide, first I'll make a little bit, and then I'll perform some experiments. But if I don't know how much I start off with, then I'm not going to be able to know which plant consumed the most carbon dioxide, right? So how do I know how much I start off with? Well, I need to react known amounts of carbon and known amounts of oxygen. Now, the oxygen I can get from the atmosphere, and the carbon I can weigh out in a dish in the lab, right? And so from the mass of carbon, I know how many moles of carbon or atoms of carbon, and from that I can know how many moles or molecules of carbon dioxide I get. Okay? So how much carbon would I have to weigh out if I wanted to get a mole of carbon?
It's on the periodic table, right? But I think you said it was 12.
That's right, it is. And we can bring up the periodic table just to see it here. But yeah, 12 grams to get 1 mole of carbon. So how many grams of oxygen should I have if I'm going to be reacting 1 mole or 12 grams of carbon?
Well, how do you know?
Well, so we've kind of learned a little bit about how to translate this into English. It's chemistry ease, but this basically says 1 unit of carbon plus 1 unit of oxygen yields 1 unit of carbon dioxide, right? 1, 1, 1. That's the balanced equation.
Yeah.
And I can also say 1 mole of each of these. 1 mole of carbon, 1 mole of oxygen yields 1 mole of carbon dioxide. So if I know I'm going to put in 12 grams of carbon, how many grams of oxygen would be consumed?
How many grams or moles?
Well, we can start with moles. If I put in 1 mole of carbon, how many moles of oxygen are going to be consumed?
1.
Now, if I have 1 mole of oxygen, how many grams of oxygen is that?
Well, it's on the periodic table. Oxygen is 16.
Okay, but is this just oxygen?
Well, it's O2.
Yeah, so that's 2 atoms of oxygen. So if I wanted to consume this thing, O2, then I wouldn't need just 16, but I'd need what?
Twice as many grams, like 32?
That's right. So the ratio is 12 grams of carbon for every 32 grams of oxygen. And then I can also calculate how many grams of carbon dioxide that would produce. I can do that calculation because of the law of conservation of mass, obviously. So it's going to be the 32 plus the 12. But I can also just know that I have a 1-to-1-to-1 ratio here again. So I'm going to produce 1 mole of carbon dioxide. And I can find out the mass of 1 mole of carbon dioxide simply by adding up the grams of carbon and the grams of oxygen using the periodic table, which is 12 plus 16 twice. Okay, so that's another way of looking and seeing the 44. Okay.